Okay, welcome everyone to the Python Anywhere room for Thursday morning of EuroPython. And first up we have Abraham Martin, who's going to tell us about architecture of a cloud hosting service using Python technologies.
Hello everyone, I'm Abraham Martin. I work for the University of Cambridge, as you may have guessed from the huge logo in the screen. I was thinking about making a little introduction, and I thought everyone knows what the University of Cambridge is, so I think I have little to say about that. And I thought I can show you some pretty pictures so you can invite me where I live and this pretty place and where I work. This nice architecture, these nice rivers where you can punt with your friends during summer, well, the 2 days of summers we have a year. The classic math bridge, and as you may know, we have a lot of clever people there, some Nobel Prizes, people that usually walk around the city dressed like this, which are guns. It seems weird, but you really see, look at, when you go there, you really see these people walking around, academics. This seems pretty classic, pretty old, but we also have pretty nice new buildings, like this one, which is the new university data center, which is one of the top data centers in the UK. It's pretty big, it's green, we have a lot of innovation inside it. We even have a HPC service, which has, in 2003, was the second most green computer in the top 500. So it's not just classic building and architecture, we also have some cool things. This is the computer lab where I used to work. I did my relationship with the university started with the computer lab while I was doing my PhD, and then I worked there as a postdoc. This building is called William Gates Building because Bill Gates paid for the half of the building. And I work on this building now, which is the University Computing Service, where we provide IT services for the rest of the university. Both buildings share a common history. And they used to be the mathematical laboratory where this machine, Brownie points, if you know what it is, it's the exact computer, one of the first computers in the world based on the von Neumann architecture, was built there. We still have some pieces in the computer lab as a museum. But also other things were built there, and in the part that I'm working now, which is the University Computing Service, like Exim, which you probably know about because still 50% of mail servers use it. So we have pretty cool people working there. I'm not of any of them, but we have some pretty cool people that also work in a lot of open source projects. So what I want to explain you today is one service that was proposed a lot of years ago, which is the Managed Web Service, and was born to solve a problem. We have a lot of researchers in the university, as you may know, and a lot of them usually hold a conference, they do research, they want to do some simple website with some statistics, show results from the research, or either do questionnaires, etc., etc. So they end up using their own web servers under the desk. It was a cheap computer that was running under the desk. It was not maintained, usually, because the academics usually use that computer for the conference, and then they left this computer under the desk. The software was not updated, and then we get security problems. We get servers hacked, etc., etc., you know. So the proposal that the IT services and the university did for solving that problem was centralizing these web services. So the solution was to provide a service where you don't have to worry about maintaining the OS or the software. You only have to worry about maintaining the web application. So we maintain the OS. We give basic web hosting capabilities like external services does. You don't have to worry about backups, and you have some dedicated resources to your web app. So that's very, very old. And when I say old, it's like 15 years ago. The first version of the managed web service was using a Solaris 7 running in a Solaris machine. So you can see that it was using a very old version of Apache, PHP, MySQL, and it was using a chroot system to maintain the separation between these different web pages. The second version came sooner than the other one, provided a new software, like Solaris 10, Apache 2, more new software, and I started to use Solaris Zones, which Solaris Zones is a kind of a virtualization inside a Solaris machine. It's kind of a container. So we were using containers before it was cool, but it's still pretty old. It also had like more enhanced features, like database-driven scripts, so you could doing scripts based on some information in the database, so it's centralized, it's better to manage, some NIS and NFS server, very classic, ZFS file system, so it provides also snapshots, which is good, and the users were able to create vhost, aliases, etc. But the problem was everything is manual, so the users have to send us an email saying, I want this, and then we make the changes, we execute the scripts make the changes, but everything is manual, so we need a lot of human intervention. So when it started to grow, we currently now have more than 200 users and more than 400 websites. It started to become a little bit difficult to manage because it requires a lot of time. So before we ended up making a new version of the managed web service, another solution was in parallel, which is the Falcon service, which is Plone-based. You only get a Plone instance. You don't get access to a server or anything. It's just a CMS as a service. And we also have like 200 websites there. So if you go to any university website, you probably will end up in either a Falcon service or a managed web service. So, for example, one of the most visited websites inside this service is the Stephen Hawking's website. So we decided to make from scratch a new service, so restart what we have done, because we don't have more Solaris machines. Solaris machines are rooting, and they're pretty old. We don't have a replacement for that. So, and we also thought, let's do more automation. We can do more automation, so it requires less time from us. So we decided to go to the classic dedicated VMs, but still maintain the same things that was proposed by the previous ones, like no root access for users, and everything is maintained by us. And when I say by us, I mean by Ansible, because we don't touch anything, but we will see that later. And so to end up these emails that comes to our inbox saying, can you please install this package? Can you please install this? We created a web panel using Django where we delegate some power to the users, so the users can do things without having root access or anything. So architecture is basically a Debian 8 machine. We install the basic packages that we have been installing up to now, like the Apache, MySQL, PHP, which is the most common features demand. But we also support other mods available, Apache available, like ModWhiskey if you want to install Python or Django, etc. We have also a list of system packages that you can install and that are pre-approved, so you don't end up with a machine with a lot of packages that you don't need or that are strange to need. And we give them all the power to do authorization to the sites, create vhost, apply for domain names, install TLS certificates in the machines, do the backups from them, password resets, power management, etc., etc. So we give them the power to do a lot of things that we were doing before. So they have a panel. Don't blame me for the design. It's an in-house design. If you visit any Cambridge website, you will see that all of them look exactly the same. So it's just a panel with some options to manage your site. So when you create a site, you get this web panel based on Django. You have some options to create vhost, ask for domain names, etc. And you get an extra VM, which is a test server. So you can clone your production server to the test server. You can test things there without having to compromise your production server. So that's good, especially for people that have Drupal installed in the managed web servers. When they Drupal, really bad things happen. So it's better that you can test it before, and if it goes right, you clone it back to the production server. So architecture looks like that. We will go one by one to see how we build it. Be aware that this did not talk about OpenStack, neither about Docker, so don't expect any of that. But we use most of them are Python technologies, and we did that project in a few months, where it's still not finished. We are still working on it, but most of it, we have done it by using 1.2, 1.3 FTEs. So it's not much people, so the amount of resources that you require for doing it, although it seems like a huge service, it's not that big. So we have here the VM architecture. Here, the VM is separated, the VM service is separated from the rest of the stack. So we start describing the VM architecture. The VM architecture is just a VMware solution. You may know these VMware solutions. It's just a ESXi servers, and you can manage these XCI servers using vSphere control panel and some APIs. And we have external backup server where we do the backups, but it's not replicated. So if something happens, then we rebuild the VM and recover the things from the backup server. So the flow is easy. A user enters to the Django web panel, authenticates, so we know who he is, and then he asks for a new managed web server. A host name and an IP 6 and 4 are allocated to this site. The VM API creates a new VM. The VM API installs the OS, and when the OS is ready, Ansible is executed, and Ansible is the one that configures the whole machine. So we are using Ansible as a configuration management, and it does everything we need. For those that doesn't know Ansible, it's just a bunch of things together. They are easy to script, so it's very easy to understand what they are doing. And they separate into folders, which is really good, and you can find the file that you are looking for, and there is separation of things in the different files that you can see. So it's pretty good to use. It also has inventory, so you can define all your servers based on dynamically or static, so you can have a file with all your servers, or you can inject the output from another API as a list of servers you have, or even the database, etc. So it's pretty nice. It works really well. And it's based on playbooks. Playbooks is just a bunch of roles linked to a bunch of targets. So you have a roles, and definition of role is things you want to install in this role, in these machines that have this role, and then you have targets, and then you say this target, these machines, I want to install this role, for example, a web server. Web server can be a role, and the web server role has a lot of tasks that install Apache, configure Apache, etc., etc. This is an Ansible playbook. As I said before, you define the host where you want to install things, and then you define the roles that these machines in this list will have. For each role, you have tasks, templates, which are Jinja 2 templates, scripts, handles, and variables. You can have also global variables or variables entering into the script. And this is how a role looks like. It's just a bunch of tasks inside the role. You can see that here we're installing packages. It's a YAML file, as you can see. And it's pretty easy to understand what you are doing. So if you have you're working with more people, it's easy to modify the file, change the configuration, etc. You can see here that the templates can be used with variables, Jinja2 templates. We use variables there, and therefore we use the same templates for all the configurations of all machines. You also have handlers, which are basically callbacks. When some function in Ansible is executed, then you have a callback later, and you can, for example, if you have updated the Apache configuration or your Django app, you can restart Apache, and the callback is cool. So this is from the VM part. We use this VMware infrastructure. We use the APIs. We launch it. We create the VM. Everything is good after that, after Ansible configures the machine. And then we can offer the service to the user. So if we start from the top of the stack with the authentication part, we have our own authentication. We use Raven. Raven is our authentication service. So you can see that we have a lot of services interconnected using a lot of APIs. It is based on a WebAuth API. And we have to build a custom Django backend. But this could be substituted by any authentication that you can use. You can use the Django one if you want. You can link with your own enterprise if you want, et cetera, et cetera. So the second layer is authorization. We have like a kind of an LDAP-ish service. It's called Lookup. And then what we have there is just a list of users and a list of groups. We can see these users if they belong to which institutions they belong to, which groups they belong to. So the end user can configure their MWS server based on this list. They can search for another users, authorize them as administrators, authorize by groups, etc. So it's just a basic list. We use that instead of using the Django groups because it's more useful for us because people is using the university to this LDAP service that we have. So they create the groups there, and they are automatically updated if someone leaves, etc., etc. So when the user has authorized the user, another user to enter to the machine or use the service, we need to still to install the user into the machine. So we have another service over there called Jagto, which provides more information about users. It's like a user identity management. So we get from Jagto a unique UID from the user. We need that because if we install the same user in different machines, we still need to identify the files that belong to him or to her in different machines. So they have the same Unix UID, and we use this Unix UID in all the user installs. User is installed using Ansible as well. It's installed in all the VMs where it is authorized. And we have periodic refreshes to refresh the lookup groups we have authorized. So if the groups change, people different change. And we allow people to upload their own SSH keys. And the SSH keys is also installed in the user configuration. So they can enter either using their password, which is checked with this LDAP server, or either the SSH that they have installed in the panel. So once they can access to the Django panel and they have the user installed in the VM, they can already access the machine. Everything is configured for them, so they can start using it. For previously, we had also another communication with the IP register API, which is on the bottom there. And this allows us, this is another external service. So as you can see, we have the main service, and then we have a lot of other services that we communicate with, which provides the university a registration for Kamakak domains. So if you want to register a new Kamakak domain, for example, importantstudies.kamakak, you can launch an API. We launch an API request using the same Django panel. Django panel sends the request, and then we get the domain name alias for that site. So everything is configured automatically. The user doesn't have to worry about the process, the internal processes. This API tells us if the user is authorized for that domain name, or if this domain name is already in use, etc. And the same API also provides us from IP addresses. We have to pre-allocate some IP addresses together with the host name. So when the user requests a new site, he can access directly using the domain name without having to wait for a DNS refresh. So what we do is just pre-allocate some addresses, and then when the user gets their site, they can access directly using the host name without waiting for a DNS update. We use 2 IP addresses. We have one host name as well as a host address. So the communications for the host, and another for the service. So if we want to move the service to another machine, we can do it without having to modify the host name or the host of the machine. So we can separate what is the service and what is the host, and we can move the service IP. And you will see this is useful later. Additionally, we have SSHFP records and DNSSEC. Anyone knows what SSHFP record stands for? No one. Good. This is to forget about that. I'm sure pretty much you all have seen this screen like that. And what it does is you can upload an SSHFP record into the DNS with your public host key, and then and if you have DNSSEC activated, you don't have to check the host fingerprint manually, because the DNS server does it for you. It gives you, the DNSSEC gives you the fingerprint, and then when you connect, you check that this fingerprint is the one that is in the DNS server, which is secure communicating with you, and then you don't have to check manually if the fingerprint or the machine you are connecting is the one that it's claiming to be. So that's pretty useful. As I said, we have a lot of services in the same architecture. We have an inventory there, which is using another API. It's based on JSON API, on pull, consume. So we give to this service called BES the data of all our services, so we can use it as an external database as well. When we know where all VMs are, we know where they are located, the IP address they have, et cetera, so it can be used even as an inventory for Ansible, or it can be used for other purposes. So as you saw, we have a lot of APIs, different ways of accessing APIs. We use SSH APIs, REST, non-REST, HTTPS, using JSON, non-JSON. But we have to deal with a lot of them in an async way, because we don't want Django, the main thread of Django, be stopped by that. So what we do is executing as a background processes using either cron jobs, which is the easy way if you don't need the API executed just after the user has launched the petition, or if you want the execution schedule, you can use Celery and Redis, which is what we use. Celery is pretty good for us because it works pretty well with Django. It's very easy to configure. You just have to add on the top of the function. You just have to declare that it's a shared task. You can use different templates like this task with failure. You can define the red tree, the number of red trees. You define the template, so you can define if it fails to log something or send you an email, et cetera, et cetera. So it's pretty easy to configure, and it works pretty well. And you can also execute cron jobs from the same Celery. It's called Celery Beat. It's a bit different, but the jobs are you just configure it as it was a cron job. So it's pretty useful for us. It works well, and this architecture, this Celery, these APIs and these services are supporting all of this, all Ansible driven. So the changes are done in Django. Django stores these changes in the database, and then Ansible is executed, takes these changes from the database, and then it executes these changes on the VMs. So we had this service. We went to the community in the university. We made a workshop, and we said, we have this for you. We thought that you will like it. And they said, we will like it, but what about if the service fails? And then we thought, well, we have a backup. You can recover for the backup. it won't take too much. We create the VM, etc. And then they say, but I need an SLA if I want to switch to you. But we didn't have an SLA because we had a backup, we have a plan, but we didn't have we didn't thought about what happens if 300 VMs failed on the same time, which requires a lot of time to recreate and a lot of time to take from backups. So some of the people were saying, we are thinking to change into MWS3, but only if you provide high availability. So lucky for us, we designed the application so it can cope with different VM architectures, which is good because you don't have to worry about the VM architecture that architecture that you are using because you are creating the VM using an API, which may be this one that we are providing, or could be an Amazon EC2 server. And then we execute everything through Ansible. Ansible only needs an SSH connection, so it's pretty easy. So we just need to replace this component, which is the VM architecture. So we thought, okay, let's update VMware with high availability. And then we saw that we need replicated vSphere, replicated storage, which we didn't have, and replicated storage for a lot of servers is very expensive to maintain because you need to a huge file storage that is shared between all the VMs. So we had a lot of things pending from this architecture, so we thought that's pretty risky for the low time we have. Better take another architecture because it's still it's also expensive to acquire all the hardware and software that we need, etc. So we decided, okay, we don't want to maintain a huge shared file system. So what we do is replicate each one of the VMs file system to another one. So we thought we can use the VMware, still use the VMware infrastructure. We add a pacemaker chorusing, which is basically a cluster that checks that all the VMs are in contact with each other and then can change the service network configuration. This is why it's useful to have service network configuration to any of these two production VMs. So we have a replicated VM. The second one, the second column, is just a VM that is waiting in something fails to be changed and I start acting as the active VM of the cluster. And then we replicated the storage individually for each one of the VMs using the RBD, which is basically a driver that sends all the writes of a machine into the other VM. So the storage is replicated to the second one, and the pacemaker takes care that if some of the components fail, the switchover is made automatically, so we don't have to worry about it. But then we thought, this is maintaining a lot of clusters. We may end up with one cluster for each one of the VMs that we're going to have, because for each one of the VMs, we will have to have a pacemaker cluster, and this is very expensive to maintain, and it may fail. If we need to execute Ansible, we need to execute Ansible in both sides, in the two VMs, so they are synchronized. So that's a lot of work, and it's going to break quite easily. So we thought, okay, let's start from scratch. We move away from VMware, and we decided to use Xen. Xen can be configured very similarly as the VMware. So you can see there are two Xen servers there. They are also executed pacemaker and chorusing, but the difference is we don't do clustering for each one of the VMs. We do clustering for each one of the Xen servers. The Xen servers have a lot of VMs inside. So if something happens with one of the servers, the whole server and all the VMs that are inside one of the Xen servers that you can see on the top, all the Xen VMs that have a Xen server are automatically migrated, live migration, to the second one. And you don't notice anything. Even the sockets are kept open. You don't notice that the switchover has happened. With the VMware solutions, you will have to wait until we restart the VM, for example, and that kind of stuff. With Xen, you don't notice anything. You just don't see that nothing has happened. So, but inside, you have changed your VM from one Xen server to the other, but it's completely transparent to you. So for doing that, it's a bit more complicated because this is the file system that we had to use. This is a very complex file system where you have all the disks. These disks are tied together in a physical volume. And then you have the left one is the DOM0, which is basically the operating system that is running in the Zen server. And then each one of these are each one of the individual Zen hosts. So you have all the storage replicated to the other Zen server, which provide this live migration. So we had a happy transition. It's working well now. But the architecture is the same, because we designed the architecture so we could change the VM provider, but just changing the API. The API is a middle API, so we only had to write an API for the Zen server, and then execute everything was exactly the same. So we are happy with that. Seems people may be happy with that as well. And we changed it from the VMware solution to the Zen solution, which is 3 node clusters. The node clusters are in different locations. We can do live migration, so the users don't need anything. It's still using Ansible. And we also use Ansible to deploy more clusters. So this is an example of the Zen server clusters. We can deploy many of them. It is easy to deploy because it's Ansible. So if we want to create more Zen server clusters, it's just as easy as get the machine, the physical machine, start it, and launch Ansible. So it's pretty easy. Let's talk 1 minute about security, because we like security. Well, I am not an expert in security. We like to enforce security to our users, so we don't end up with problems. We decided to not use root passwords when we create the Zen host, so the people, we don't have to manage root passwords, which is difficult to secure a lot of root passwords in a database. We don't want to manage that way, so we only use keys. We connect to the machines using keys, Ansible connect to the machines using keys, etc. We have a separation of privilege. For example, we need to pre-generate the host keys of the Zen host. The host needs to be generated previously because we need to upload the SSHFP records before even the machine is created. So we need to have a pool of host keys that we can use in the future and we can install in the machines. And we use user service, which provides a useful interface. So users can execute commands from root users or other more privileged users based on some filtering and some templating. And we also provide a TLS certificate service. This is an additional one, because we want to follow one of the new initiatives from the FFF and the Mozilla and AKMA, which is HTTPS everywhere, or Let's Encrypt. Let's Encrypt is an open source CA, which provides you with a free certificates for your web page. HTTPS everywhere is EFF trying to force everyone to have HTTPS web servers. And even the HTTP2 specification doesn't include to enforce HTTPS, but a lot of people are saying, well, when we move to HTTP2, everyone is going to be HTTPS. That's not really true, but because the specification doesn't say it, but all the implementations from Microsoft in Internet Explorer, and Mozilla, and Google in Chrome only implemented HTTP2 if it uses HTTPS. So we like it to test our servers. I encourage you to do the same. If you enter to the SSL Labs, you can get a qualification how secure is your web server, which is pretty good because it gives you some hints of if you have any openback, all the specification, all the version of OpenSSL, etc., etc. And apart from security, changing topics, we use also some metrics and logging systems. So we can have users, we can give users some information about how their host works. For example, we use a metrics service, which is basically a statsd and collectd in each one of the machines installed, also using Ansible. We have a cluster of message brokers that get this information from all the hosts. And then we have a cluster of carbon graphite, which store this information gathered from all the machines. So the user can see these graphs in their panel, the web panel, and they can see how the machine is behaving, et cetera, et cetera. And we are now trying to implement Logstash, Elasticsearch, and Kibana, which also provides information about the hosting, the web server, and how it behaves, where do you have the visits, how it behaves during different periods of time, etc. So you can have a lot of logs gathered by Logstash stored in Elasticsearch and then showed in a Kibana. So that's pretty much all I wanted to talk about. I hope you like it. Thank you.
Thank you, Abraham. And we have a few minutes for questions. Any questions? Yes?
Why did you choose Shen instead of KVM, for instance? I mean, what made you choose one thing and not the other?
This was a long discussion we had between the developers, which is basically three. We didn't have any strong reason to choose one or the other. We saw, doing a little bit of research, that Shen worked a little bit better with DRPD, which is one of the main components we wanted to use, because we wanted to do the replication of storage from one Zen server to the other. So we saw that it was integrated inside the same Zen server, and we decided to go that way. But we could have chosen KVM. It was in the list of products that we had to research and decide.
Hi, thank you for the talk. It was really fun, but to be honest, I didn't really understand the subtleties in the last architecture, because you had several hard drives and that you have several Zen servers that actually overlapped on several drives. So were they virtual servers or?
Yes. So this, the whole picture. So this is the picture of the VM architecture on the top. This is more the view of the file storage. This is a single machine with a RAID of disks. And this is a file storage for a single machine. So you have the physical volume, and then you have the first column is where it used to be DOM. It's called DOM0, which is the operating system that manages all the VMs. When you access to the Zen server, you access to this. It's also a VM, but you access to this, and it has direct access to the hardware instead of the VMs, which have access to the hypervisor. And all the other columns, each one of them, are a Zen host, which are one of these VMs, or DOM-U, as it's called in Zen. And each one of them has the DRBD device, which is basically a virtual block device, which is replicated from here to another DRBD server. So you have each one of these DR devices are inside this list of virtual block devices, and they are replicated through the network in real time when they are written or read, only written because it's a sync, to the secondary Zen server. So it's done automatically through the network when it's executed, but the difference is each one of them has a DR device.
Okay, thank you.
Okay, we have maybe 1 minute if anyone has a really quick question. No? Okay, please join me in thanking Abraham once again.
Hey man. Yeah.
If you prefer, we have bottles
Oh yeah.
from here.
I'm alright. I don't want to knock it over. That. Nah, I'll knock it over and go everywhere. Let's not do that.
No.
Nah, it's too dodgy. Very kind there. Water on the laptop could be suboptimal.
We have power,
Yeah, I'm okay. with battery.
sound. if
I
you
do need internet though. That would be handy. You got a network cable hiding somewhere here? I saw it the other day. It's that grey one, isn't it?
Sound, you say that you don't need. Do you prefer these microphones
Yeah.
or
Let's go with this.
you have
No,
the
yeah.
other
This.
one?
Oh, I might use this thing. Where's the little laser pointer? Oh, there you go. Now.
The pointer
Yeah,
runs
I like
when
that.
you remove the key.
Okay, cool.
If you also want to use these ones to move,
Yeah, I can. Yeah.
you have to put it.
That looks good.
Do you want to allow questions when you finish your talk?
Yeah.
Okay.
So hopefully, what, 35 minutes talking?
Yes. You have
Preview.
you start now, and at 12.10 the girl starts showing you those papers. And
Yes.
then you should finish to 12.20 to start questions.
After 35 minutes.
Yes.
Yeah, that's it. That's
Okay.
it. Let's do a test. Oh shit. Hey. Oh, good to see you. Oh, yeah, yeah. I realise who you now. I realise who you are now. Yes. Yeah, that is. Oh, sorry. Yep. Yeah. I don't know if the internet's working here. I'm getting resolving host. I'm on. Oh, well, I just need to click that, do I? Let's try again. Yeah, this Ethernet doesn't seem. No, the Ethernet doesn't.
¿Hay algún problema con el internet del cable de la sala?
If you could just pause your BitTorrent clients for the duration of this talk, we'd really appreciate it.
Oh, yeah, I've got one of those. Is this like plugged in?
Ya me estaba contando de ello.
I think that's okay now.
Yo he preguntado por radio, no tengo respuestas.
Yeah.
Sí, suele haber, tienen problemas. Sí, vale. Muy bien. Vale, gracias. Sí. Muy bien. Vale, gracias.
All right. Thank you for coming. And now we're going to hear from Tom Viner about testing with two failure-seeking missiles, fuzzing and property-based testing.
Thank you. Okay, yeah, so today I'm going to tell you about property-based testing, fuzzing, and I'm calling this, tongue-in-cheek, failure-seeking missiles. So I'm here to challenge how you test your code. Let's see where the audience is as a starting point. Hands up if you've written a test. Okay. Hands up if you've only used hard-coded values as example data to pass into your code. Fair enough. Hands up if you've used some sort of random input. Good. Hands up if you've used property-based testing. And hands up if you've done any fuzzing. Okay, good. So yeah, some good things to learn about today then. So I'm here to ask you, are you testing your code hard enough? Are you stretching it? Are you asking it questions it wasn't expecting? Are you an aggressive interviewer? Are you a softball interviewer who asks the easy questions? She wasn't expecting that question. And maybe you should ask your code some questions it's not expecting. So what are we trying to achieve with our test input data? Possible goals, well, to start off with, you want to cover the happy path. That's the one that's going to earn you some money and get the job done, but that's the absolute minimum. You probably want to cover all of the code base. You want to cover so exception handling and the validation when the user passes you some data that you understand not to be valid. But what about unhandled exceptions? By definition, you're not expecting them, so how are you going to think up examples for that data? If you knew what they were, you probably would have caught them already. And then not just covering each line of code, but you really want to cover the independent paths through your code base. It's going to start sounding like a lot of work, isn't it? So I'd like to just ask you to take a moment to think about the data that you pass into the test that you've written. This is to help you contemplate. So which type of points do you pick when you're writing your example data? And where would an adversarial approach take you? I'm not an artist, but Google image search is quite handy. So this is an artist impression of the central parts of the input space here, maybe the obvious examples, jane@example.com. But maybe you're under-testing some more difficult examples. I've certainly seen Unicode errors that would have been caught if example data had included a Unicode snowman or something like that. Also, just passing in empty lists, empty strings, it's good as a base standard for edge case testing. So how do we create test data? We can write hard-coded values, like most of us have done. We can create purely random data, just with no feedback. So Model Mummy does this, just gives you something conveniently random that will get the job done. Or by firing a failure-seeking missile. Boom. Hardcore, let's take a closer look. Okay, so Quick Check is a Haskell library. Don't boo it just yet. So it's been around for a while. Hands up if you've heard of it. Cool. So this is property-based testing. You specify a property of your code that must hold, and Quick Check will quickly check if it can prove you wrong. It does its best to find a counterexample. So this is a little bit of Haskell. So the basic thing to take away here is that two lists of integers go into a property, and a Boolean comes out that is whether this property holds or not. So it's about reversing lists of integers. So basically, imagine 4 integers, a list of 4 integers, and a fist of 4 interfingers here. And it's saying you're going to join them and reverse them, as opposed to reversing them and joining them. Okay, so it's a slightly dubious proposition, but we're going to see if it can prove it wrong. And at the bottom there, you can see 0 and 1 as the inputs after some shrinking, and it has proved it wrong. But this isn't Euro-Haskell monad-con, so let's not accidentally learn too much Haskell. Instead, let's find out what functional language developers think of our world. This is a direct quote. In an imperative language, you have no guarantee that a simple function that should just crunch some numbers won't burn your house down, kidnap your dog, and scratch your car with a potato while crunching those numbers. Fair enough, but we like Python anyway. So Hypothesis is the Python version of QuickCheck. It's more of an update because it adds some new features. Let's delve into the kidnap dog world of Python. So just as a reminder, this was the Haskell version. In Python, there isn't a function that reverses lists, so I've made one here. And in a similar way, you can see the @given decorator here specifies 2 lists of integers, which map to the 2 inputs to the test function. And then at the bottom, you can see the property is defined just with a standard assert. We're running it with a PyTest runner, and there's a little tiny Hypothesis PyTest plugin that just helps you see the output a bit clearer. So it proves it wrong, and it actually comes up with the same counterexample that QuickCheck did. And we didn't have to think up any example data ourselves, so that was an improvement. So what's going on here? How could this be working? So maybe it's doing a formal proof in the background. Maybe it's doing some sort of static analysis. Maybe it just passes a symbol into the top of the program, looks at all the manipulations, ends up with a formula, and then solves that formula. No, even for mathematicians, they haven't quite got there yet. I tweeted a really interesting article called Will Computers Redefine the Roots of Math? A Wired article. But no, they're not there yet. Mathematicians still have a job. And same in computer science. They haven't really managed to, especially not in Python. So that leaves us trying a crud ton of examples, also known as fuzzing. That's what's really happening. Let's have a look at the dirtiness under the covers. Okay, so this is the first list of integers that Hypothesis is sending in. If I go over here. They're pretty nasty, and it turns out proposition is false, fine. And so basically it's proved it wrong in the first hit, but it doesn't want to show you that because that's kind of ugly, and I don't think that would pass code review if you tried to put that as a hard-coded example. So it has a go at making it simpler. As we scroll down here, you can see the first list is getting shorter. It's only got 3 items now. It's worked out that big numbers are more annoying than little numbers. So those numbers at the top there are getting shorter, just 2 numbers. 1 number, keep on going. And the second list will get shorter as you get down, and it's getting it. And it actually overshoots. You get something so simple that when you reverse it in each way, it's actually true. So that's bad, doesn't want to show you that. Simple, try some empty lists, and this is the simplest one it could come up with, and then that's the one it ultimately shows you. So that's the one you copy-paste into your deterministic code base, into your test set. As an aside, if you run that again, it won't go through the whole business of those massive list of integers because it's got a local database of successful examples. So that's kind of mainly for a speed enhancement, but also if it's searched really hard and maybe there's a bit of luck that it's found a counterexample, it wants to keep onto that because it might not find it next time, theoretically. So what's going on here? It's generating random-esque input data. So it's not purely random. It's random, but with a view to breaking your code. It runs the test repeatedly, so it's really worth bearing in mind this is not like a standard unit test that just gets run once. That @given decorator means that that test actually gets run by default 200 times, or at least until a falsifying example has been found. If it finds a counterexample, it will then try and shrink that to the best of its abilities, just to give you the cleanest, simplest counterexample to prove your property wrong. So let's have a look at that random-esque data. Where did the integers come from? So this was the decorator. So this is strategies.list and strategies.integers. And the integer strategy is made up of two parts. The random geometric int strategy is basically saying, give me smallish numbers, like maybe 0, maybe -1, maybe 17 will break your code. And the other one, the wide range, says, well, I'm going to give you basically any random number from like anything that your Python interpreter can handle, so massive integers, and just, maybe that will upset it a bit. These are strategies to they are relentlessly devious plans to break your program. And the list strategy is to say this, you pass it the elements you want in your list, and it averages at 25 elements, but you can set it to maximum size, minimum size. It's got sensible defaults, but you can override them if you need to. So Raymond Hettinger tweeted this, calling it so you might not know what the % does, it's the remainder upon division. And he has suggested two properties that should hold. The result should have the same sign as y, and the absolute result should be less than the absolute of y. Okay, well, let's check. This is how we would write that. So there's no list of integers, there's just two integers here. And they relate to the xy inputs to the test function. So we've got a new function here, assume. This is a way of giving feedback back to hypothesis, and it says, if this assumption it proves false, in other words, if you give me a y that's 0, stop the test, it's not appropriate, and don't give me any more like that. Okay? And so in that way, it's guiding itself to be more helpful, give you inputs that are more likely to be relevant. So we calculate the result, and I had to create a same sign function, but apart from that, it pretty much reads as English or copy and paste from the tweet. Let's see what the answer was. It passed. Okay, I should know better than doubting Raymond Hettinger, but I can and will property test his tweet. How does it do it? So the data strategies are probability distributions to pick elements from within that distribution. There's guided feedback via assume. Shrinking of counterexamples to be clearer to read and easy to understand why they're breaking your property. And a database of failing examples for speed, especially when you're doing TDD. If it finds something wrong with your code, you've broken a property, you can have a go at fixing it, and it will try it straight away again until you make it pass. The internals of hypothesis are really interesting. I won't explain them. They use a parameter system. It's worth having a read up. He's got a good page on the documentation about that. Let's look at one more strategy. So we've seen integers. The floats are a bit more complicated. If you claim that your function accepts floating point numbers, it's going to do all these mathy sounding things, Gaussian, bounded, exponential, maybe just some integers. You weren't expecting that, were you? And then some nasty floats as well, so 0, minus whatever, minus infinity, positive infinity, nan. You can assume these away if you don't want them, because if you're doing maths, they will probably break your code. There's some great advanced features of hypothesis. It makes it very easy to take the built-in strategies and make your own strategies. So say you've got a function that accepts a comma-separated list of integers. You could map a list of integers, have them joined by comma, and then pass that into your code. Because you want your test data to be relevant to your test. It can't just all fail at the first hurdle because it's too random. So you might want to build your own strategy like that. There's plugins for Django, a bit like Model Mummy or Factory Boy, and NumPy as well, that's prototype. There's also a bit experimental, but a stateful testing, where you give Hypothesis the controls to your program, and it tries to find a sequence of actions which cause a test failure. So, I don't know, this sounds very interesting to me. Then moving on. Let's look at another failure-seeking missile that's getting a lot of attention recently. So American Fuzzy Lop, this is a fuzzer, second version. The first one was called Bunny the Fuzzer, so I think Michael Zalewski likes rabbits, and they're certainly fuzzy. So it specializes in security and binary formats. Low-level libraries are essential to everything we do, whether it be accessing a database, image processing, encryption. So we'll get onto the Python AFL in a minute, but just for a moment, let's think at the C level. So just to remind you, a fuzzer is something that fires data at your program, attempting to crash it. So we've kind of moved on from property-based testing. This is more about crashing your code than specifying properties. So these are things that you want to leave running for a good while, maybe on multiple cores. And speed is very important because the more ground you cover, the more likely you are to find some interesting inputs. So fuzz testing has been around for a couple of decades or more. There's fuzz backwards, Zuff, that people have been using for a good while. And AFL is kind of a new style with some guiding going on. But traditional fuzzing is not dead. This is very important. AFL might be the new cool thing that came out last year, but Google has been running fuzzing against FFmpeg for a couple of years and found 1,000 bugs. Literally 1,000 commits fixing those bugs, so not to be sniffed at. So if you don't know, FFmpeg is a video processing library. It's in Chrome. It's probably in your local video player that you have on your Ubuntu desktop. So the strategy was take small video examples, small video files, mash them together with mutation algorithms, maybe splice them together, mutate some bits or bytes here and there. And then, admittedly, they had 500 and then eventually 2,000 cores over a period of 2 years, so maybe not just your laptop. But they found they made great progress. A lot of memory management bugs were found. Actually, I was speaking to one of the FFmpeg developers last night, and I can confirm it's not just because they've written awful code. It's just because this is quite a hard thing to do. The video specifications can be 600 pages long, and they have to write very, very fast code. That's why they don't write it in Python. They have to look after all their memory management, and it's very easy to not do that perfectly. Now, there's a quote on that blog post where they thought 20 to 30% of the problems found could easily be exploitable. So there's 100 to 200 zero-day exploits that they found with that fuzzing. So something tells me the local security services and/or hackers, this would be a good approach they might be doing. Let's hope the good guys find these bugs first. So AFL's goals, it does need to be very fast because it's got a lot of ground to cover. It needs to be reliable because if it breaks overnight, it's not going to get much done. I think in the past, fuzzers took a lot of configuration, but this one tries to be very simple, not require much setup. I'll show you in a minute. And it does the things traditional fuzzers do in terms of taking some sample inputs, mutating them, but it also has a little secret, which is it adds compile time instrumentation. So this means that when you compile your C code, at each branch point, it adds a little hook that records the path taken through the code. So this, like we saw earlier about code coverage and taking independent paths through the code, it's able to get feedback on where its test data travels through the code base. And you really just drop in replacements. So you might have been using GCC before, you just replace it with the AFL version. So here's a toy example. So we're literally just reading 100 characters from standard in. And the bug we're simulating is, if the input is foo, then we're going to blow up. So it's a little toy example. Let's just compile that. So there's no configure here. We're just compiling it. And when I echo into the program there, I've got some print statements. So it said 1, 2, 3, 4, and it did abort. Okay, so it works. Let's try fuzzing it. So in the on -i is the input directory. So I've got one sample input, which is literally just one file with one dot in it, just to kind of say, here's something to get going on. I'm not going to tell you what the answer is. See if you can get to the answer. There's an output directory where the results will end up. And it's worth saying, if you're on a laptop like me, you probably want to use a RAM disk because it's going to do millions of writes, and you might have your SSD stop working quicker than you thought. And it's just going to fire this test data into the standard input of our program. So this is the dashboard you get with AFL. So I'd draw your attention. I've got a laser here. So up here, we've got total paths and unique crashes. So it's found 4 paths through the code base, which was those if statements. The strategy yields down here. This gives you a sample of some of the mutation operations it's doing. So bit flips, byte flips, arithmetic. It's going to try some integers. We haven't given it a dictionary here, but I'll show you one of those in a minute. Oh, my notes have disappeared. That's helpful. Let's try that. Secret. Okay, recovered. Right. And the other thing to show you, it's done almost 1 million runs in, what's that, 2.5 minutes. Didn't want my notes to disappear, that's not helpful. Okay, next slide. So within the findings directory, you get a queue of interesting inputs that it has found take a different path through the code base. So it started with that dot I mentioned, which was my sample input. It's found that after manipulating that, it found one that started with an F. So it's clearly trying thousands and thousands of examples, but when it happened to find one that started with an F, it took a new code path. So it recorded that for reuse. Similarly, FO, FOO, so it's kind of it's kind of stepping up, making it further through the code base each time. And then in the crash directory, it's found an example input that crashes the code. So this is exactly what we'd be looking for. So let's just have a look at that crash file. So it has a kind of long file name, but it records, this is where it's recorded what's happened. So it's told you signal 6 is a SIG abort. We did the abort, so that's expected. It tells you that it's based on the third item in the queue. It's done some 8-bit arithmetic. In other words, it's replaced that Y with the umlaut with an exclamation mark. So you can kind of see how it's working. You can see how it's manipulating previous inputs. So it's able to stand on the shoulders of what it's achieved so far and get one step further. So in the last year, it's had a very, very impressive trophy case here. This is about 1/3 of the list, by the way. So there's security libraries, image libraries, SQL libraries, you name it, almost. But generally focusing on libraries that have, can be random input, but also, so you've got bash there. You have to give it some more help when you're doing a kind of non-binary input, because if it just fires, random characters at SQLite, it's not going to get very far. So let's have a look at a specific example, SQLite. It's worth saying SQLite is a very, very well-respected library in terms of testing. It has already been fuzzed by a traditional fuzzer, so you might think there's not much low-hanging fruit there. The approach taken was to start with a dictionary of SQL keywords. So you literally just put these kind of one per line in a file. They grepped out some handwritten test cases from the SQLite test base, and they found 22 crashing test cases. This is one of the simpler ones. So this ends up arriving in a function with an argument not initialized or something like that, or zero-length argument where it was expecting a list of one or more things. So these were able to be fixed. So how does it do this? Let's just see an overview. It is a great traditional fuzzer, and you can use it without the instrumentation. It will search for inputs that span different code paths, and it uses genetic algorithms to mash together the examples it's seen so far, as well as just mutating those examples one at a time. But you can imagine it's searching the input space, and it's got some help, it's got some guiding by the instrumentation, but it's always going to be a slow process because the input space can be massive. It certainly can't just go A, B, C, D and do like an exhaustive list of all inputs. That would take forever. So let's have a look at fuzzing CPython. It's worth saying that obviously the innards of Python are written in C. So this is a different proposition to fuzzing Python code, which we'll see in a minute. So you can download Python source, Mercurial. You can compile it, very similarly to as the Python docs tell you, but using the AFL CLang compiler. And you can start fuzzing it. So I've got a sample sample target program here. So I'm not a C-types expert, so I can't explain that line, the magic line that you need there, but that connects things up. And you're literally just passing standard in to JSON load. So it's treating it as a file. And we're not catching Python exceptions here, but we're looking for exceptions that happen in the C code. So I ran this overnight the other day for 8 hours. It didn't find any bugs yet. Maybe I shouldn't be so surprised. It'd be a bit easy if it was that easy. But it did run 121,000 times. It is a lot slower than just running the toy example earlier because it's loading the whole Python interpreter, etc. But there's tools within AFL to make this faster and easier. So they have a fork server, and they have various techniques you can use to make things faster. It also gives you some hints before you start about putting your operating system into performance mode instead of power-saving mode. So, you could say this is more ethical than, causing global warming by mining Bitcoin. But, yeah, certainly it can cause laptops to get a bit hot and a bit CPU intensive. OK, let's move on to Python AFL, because this is not Euro C null pointer exception conference. So this uses Cython to connect the C layer and the Python layer. It connects the instrumentation that we mentioned to the Python interpreter via sys.setTrace. So every scope that's entered will kind of log a little waypoint as traveling through the code base. And your unhandled Python exceptions get converted to SIGUSER1, which AFL will recognize as a signal. And you can see here, PyAFL fuzz is just basically you type pi before AFL fuzz, so it's literally just as easy to use. So here's an example Alex Gaynor did of using this to fuzz the cryptography library. So it's pretty simple. You have a little AFL.start hook there that connects things up. And he's literally just passing standard input to decode a signature. He said it was fruitful, but I don't know if he listed any particular bugs that he found. But this is the general approach. So what are some interesting questions raised by these two libraries? So in default mode, Hypothesis and AFL Fuzz will give you new input data every time you run them. So this could be considered annoying to some people. They want to know if a new commit fails their tests, and if you've got different test data every time, well, maybe it failed because it found a different test input rather than your commit causing it to fail. So consistent pass or fail, some people insist on. On the other hand, you might find more bugs, so that would be handy as well. So I think the resolution between the two is to do the non-deterministic testing, maybe not in your per commit testing, but to look for the counterexamples it pulls out and copy those into your deterministic test pack. Or just live with the non-determinism and find more bugs. That's what the author of Hypothesis recommends. But you can put it in deterministic mode if you insist. So we've been thinking about random inputs. One way to think about this is if things are too random, they won't even get through the starting gate. They have to be relevant to your code. On the other hand, you can't enumerate all the examples because there's too many. Your input space is often just too massive. And if you give a happy path sample input and you don't mutate it enough, then you're just going to go straight through the maze and come out the other end and you're going to think everything's fine. So you want to have that sweet spot where you're reaching your dead ends of your code base, or your dead ends of the maze, which represent all the paths through your code base, but not having them all fail at the first hurdle because they're too random. So which library should you use? Well, if you insist on just using standard unit tests, you should at least try to be more adversarial, but I would say you can't expect the unexpected, so you should probably use Hypothesis if your input data are Python structures, and even if they're not built-in data structures, you can build your own strategies. It's quite fun as well. And also it means you don't have to think up the hard-coded examples. So people say that the test code base becomes easier to read because they're not distracted by the specificity of, bob@example.com. It just says this function takes all strings or all lists of integers. And something like AFL or Python AFL, if your inputs are binary, or as we saw, maybe you're parsing text input like an SQL library. So in conclusion, we've seen two styles of test data generation. Humans are generally bad at picking random examples. Developers are bad at being adversarial to their own code bases, which they understandably love. Computers are fast, let them play with your code. And find more bugs before your customer or the Secret Service does. Let me end by saying, don't interrogate your code base like it's a fluffy bunny stuck up a tree. Fire a guided missile, blow the branches off the tree, and clear up the mess. It's not just me saying it. Celebrity endorsement. Just a little reminder there. And also of interest, you don't even have to get up. The talk after this one, which will be more informative and better presented by Moritz Skrombach, who I haven't talked to yet. I hope I didn't cover all your points, is in this room directly afterwards. And there we go. I've been Tom Viner. Any questions?
Thank you, Tom.
Thinking back to Guido's talks yesterday, is Hypothesis Python 3 ready, and could it be made to use the type annotations if they were available in the code?
I think it is Python 3 compatible, but I don't know about the type hints. You'd have to ask the author of that library. Yeah, sounds interesting though.
Thanks for the interesting talk. How does Hypothesis handle if the code under test exhibits some randomness itself? either voluntarily, maybe a Monte Carlo algorithm, or involuntarily by a mistake?
Very good question. It will raise a flaky code warning. So it will tell you that its workflow is, you can suppress the warning, I think, but it basically tells you that if your code is non-deterministic, then you're less likely to find helpful results. So you may want to put your code into deterministic mode itself, or take another approach.
I just wanted to point out, sorry, if you want to help making libraries, especially C libraries, more secure, there is a project called the Fuzzing Project by Honno Book, which helps you with some documentation to get started with AFL and fuzzing your favorite library. So that's a very good point to get started if you want to make things more secure.
Could you just repeat the name of that?
The Fuzzing Project,
Cool.
I believe.
Thanks for the talk. You mentioned that Hypothesis runs iterates over its tests many times to produce its results. Do you run it as part of your standard unit test workflow, or do you run it somewhere else in your testing workflow?
I think I personally would bite the bullet and use it in a TDD workflow. There was a talk the other day about TestMon, which uses coverage.py to only run the tests that are related to the code you're changing. So, you could get a speed improvement from TestMon and then balance that with a slowdown from Hypothesis and just maybe end up where you were before, but with finding more bugs.
I have a quick question. So, because Hypothesis is generating random input, is it a bit strange to use on a project where you have multiple developers? Because then doesn't each developer have different input into the test?
Yeah, so, the inputs are non-deterministic to start with. So, even before you had a local database of examples, everyone's getting different test inputs. This idea of sharing the database of found examples, I think, is still a work in progress. I think the developer of Hypothesis is still trying to think through whether it makes sense, to, for example, have that on your CI server, or whether that's a bit of a non-starter. You can add another decorator to tests to give them specific examples, to force it to give a specific example. So if some developer found a certain input that was helpful, they could do a commit that hard-coded that as always present.
All right. Please join me in thanking Tom once again.
estaba disculpando. Sí. Ajá. Bueno, de todas formas, no, porque este señor le está poniendo ahí de un punto de acceso. Vale. Muy bien. Vale. Sí, sí, el cable sí está puesto. Sí.
Ist das nicht lokal oder musst du auf die Datenbank irgendwie rauf? Oder was?
Aus der VM kommt man nur über das VPN ins Internet. Das
Muy
ist ein
bien.
bisschen scheiße.
Vale.
Und ich hatte eigentlich vorher alles vorbereitet und dann ging die Auflösung irgendwie daneben.
Mhm.
Hat's geklappt. Das ist echt scheiße.
The technical stuff is restarting internet. So
Mhm.
in some minutes, internet, I suppose it will be working.
Okay.
But if is, you are giving a point, access point.
Yes.
Okay.
Mobile. Ah, jetzt lädt's. Formeln kann er halt nicht.
Ja, das macht mir nichts.
Ich lasse das
Okay.
Handy mal so liegen. Hier.
Ja, danke. Please don't break. Okay, finally.
He's going to introduce you.
To say your name is Moritz Gorbach?
Moritz Kronbach.
Kronbach. Yeah. All right. Thank you, everyone, for your patience. As we're starting a little bit late, we will run a little bit later as well. And right now we have Moritz Grombach. I don't speak German, I'm sorry. Who's going to tell us more about randomized data generation for robust unit testing with What's All the Fuzz About?
Okay, so really sorry for the delay, but let's get started. My name is Moritz Kronbach. I work at Blue Yonder in Germany, and I'm going to talk about pretty much the same thing as Tom just did. I hope those who watch both talks still will find some interesting things. First, a little bit about me and why I want to talk about this topic. My job is doing predictive analytics. Basically means predicting the future, but actually it doesn't have anything to do with this. It looks more like this. We have some machine learning pipeline with data pre-processing, external data sources, and then some super secret algorithms which produce a machine learning model. We work with big data. If you do an image search for big data, you will find that big data is shiny, clean, and most importantly, blue. From my experience, big data is often not shiny and not clean. It can be very complex and dirty and nasty to work with. So it's more like this, but it's definitely blue. So big data is really a breeding ground for weird edge cases and things that can go wrong. And of course, we have to find ways to protect ourselves against these things and discover potential problems before production. And randomized testing, or I call it dynamic testing, is one such tool to help us find problems before going into production, to reduce stress for us and for our customers. Okay, so what do I mean by dynamic testing? Basically, I mean both property-based testing and fuzzing. These things are usually seen as kind of separate things, which sometimes makes sense because they are often used for very different things, but it's sometimes also sad because there are lots of cool stuff in both fields, and often it doesn't make sense to separate them. So by dynamic testing, I mean any testing where test cases are generated automatically, for example, either by fuzzing, which means the user gives some example input, which is then mutated automatically, or by parameter templates, which means the user gives some generative model from which test cases are generated. And then the function behavior is checked for properties, like does not crash, does not time out, or other universal properties like mathematical expressions that the function result should fulfill. In contrast to dynamic testing is, of course, traditional static testing, where test cases are provided by the user, and the function behavior is also precisely defined by the user. I want to compare the two types of testing a bit. For this, I want to introduce two attributes of test. The first is precision, which means how closely the expected behavior of the function is defined. And the other is case coverage, which means it's sometimes called input space coverage, and it means what proportion of the input space is covered by test cases. I've had some discussion about if case coverage matters. So, for example, does it matter if we check 5 out of 2 to the power of 64 cases, or 5,000 out of 2 to the power of 64 cases? In any case, it's still a really, really small proportion of all possible test cases. But I think it does matter, and I give one example to maybe illustrate this. So let's say you have implemented an algorithm, and there's a numerical instability in your algorithm that you don't know about, and you don't know that there could be a numerical instability. And only one in 1,000 inputs are affected by this. So if you use 5 test cases, you have a probability of about 0.5% to detect this instability. If you use 5,000 test cases, you have a probability of nearly 100% to detect this. There are other reasons, like Tom said before, the independent code path coverage can increase, which is much stronger than just branch coverage. So in general, dynamic tests help you find classes of test cases that you didn't think about before. And usually it's like this: static tests have very high precision or even perfect precision, but low case coverage, and dynamic tests have sometimes low precisions because we have to define general properties, but a bit higher case coverage. And sadly, usually you can't have both high precision and high case coverage, so the best way is often to have just one at a time. So it makes sense to use both static and dynamic testing if you want to maximize robustness. Okay, now a bit more practical. I'm going to show some examples for dynamic testing in Python, and I'm going to use hypothesis, which is quick check style testing for Python. I really like to work with Hypothesis. It's stable but still in steady development, and it has a lot of innovative features, some of which I am going to show. Okay, first example. So your colleague went on holiday and he left you this function which calculates the Fibonacci numbers. Does everyone know what the Fibonacci numbers are? I think yes. Okay, so maybe if you look at this code, it's not really clear that this formula computes the Fibonacci numbers. The Fibonacci numbers are integers, and here is some stuff with square roots and then an inverse here. So we are not really sure if this is correct, but our colleague also left us some tests. He's testing the base cases, 1 and 2 is equal to 1, and then 2 more cases which are easy to compute in your head, and even another case, FIB50, which he probably looked up on Wolfram Alpha. And we run these tests, and everything is fine. But I'm still not really trusting this code, so I'm going to write a dynamic test. For this, I will first set up Hypothesis. The most important piece of Hypothesis from the user's perspective is the given decorator, which provides a test function with automatically generated test cases. The other important piece are strategies, which define how data is generated. So here we import a strategy for generating integers. And then we import some settings stuff to de-randomize Hypothesis, because for the presentation I don't want any random behavior. And we limit the number of iterations and set a timeout. Hypothesis has a built-in example database where it stores any examples that falsified an assertion before. And every time you run your test suite again, these examples will be run too. Of course, that makes it non-deterministic, so I'm disabling this for this presentation. Okay, this is my dynamic test. Let's look at this function first. Test fib recurrence takes one parameter n, and we check that the function fulfills the recurrence that defines the Fibonacci sequence combined with the base cases. And this recurrence should hold for all values with at least 3. Let's run this. And we find that there is a falsifying example, namely n equals 71. So this assertion fails for n equals 71. Let's take a closer look first at what happened. So I added this settings parameter to given and increased the verbosity of the output. And we see that the first falsifying example is n equals 805. But Hypothesis doesn't stop at this point. It tries to find the simplest falsifying example now. And for integers, this means finding the smallest counterexample. So what it does, it starts with small values, n equals 3, 4, 5, and then does pretty much a stochastic binary search to find the smallest counterexample. So it goes up to 67 here, which still works, and then 131, which doesn't work anymore. So it goes back one step. So it tries to find the counterexample somewhere between 67 and 131. 31 now. And after a few more iterations of this, it will find the example we have seen before, namely 71. Okay, to summarize this, the first step when hypothesis runs is sampling. It generates test cases until it finds a falsifying example or until the maximum number of iterations is reached. And when it's done, when it finds a falsifying example, it tries to shrink this example, meaning it tries to find the simplest falsifying example. For integers, this is the smallest example. For strings, this is the shortest string, for example. Yeah. And we've seen two key elements of hypothesis given, which is the decorator that supplies test functions with data, and strategies which describe how data is generated. And I think we have seen that dynamic testing is very easy to implement and often very useful for math-heavy code, where you have nice, beautiful properties that describe your function's behavior. But let's do some toy example with some less mathematically elegant code. So this one. So it's really just a toy example. We want to test the quote function from the URL lib package. The quote function prepares a string to be used in a URL. So you can see here, it encodes the space with %20. And we can run this static test, and of course it passes. To write a dynamic test for this, we have to think, what do we expect from the quote function? What are properties that the quote function should fulfill for any input? And one thing we might expect is that when quoting and then unquoting, no information is lost. So if you quote a string and then unquote it again, you would expect to get the original string back. Let's try this. And we find a falsifying example. So have we found a bug in URL lib? Sadly not, or maybe not sadly. But anyway, we just weren't careful about what kind of input we generate. The text strategy generates strings consisting of all possible Unicode characters. And the counterexample we found here is just a control character, so it doesn't make sense to encode this in URLs. We can easily fix this one. We import the string module and pass the parameter alphabet to the text strategy and tell it that we only want printable characters. And now it seems to work fine. Okay, but in general, handling impure objects like strings and datetimes can be a bit challenging, not only in data generation, but also in your assertions, because often the underlying functions have a lot of special cases that you somehow need to handle. I just want to give you a quick overview of what kind of tools there are available to assist you with this. Hypothesis has some things built in to help you. For example, the alphabets for string generation. For datetimes, there's the hypothesis datetime package. Who knows what the fake factory package does? Okay, 2 persons. The fake factory package is really cool, I think. You can generate all kinds of everyday fake data. Like you can generate random URLs, random phone numbers, random email addresses. And Hypothesis Fake Factory exposes these random generators to Hypothesis. So you can, for example, test functions that take a URL as a parameter. Hypothesis has also built-in support for custom strategies. So you can create your own strategies, for example, by mapping existing data types, so basic data types, to your own custom data types. Yeah, that was quick. Just to summarize, dynamic tests increase case coverage at the cost of precision. Dynamic and static testing complements each other. None is a replacement of the other. And sometimes it makes sense to use both. Sometimes it's better, more pragmatic to just use one of them. For math-heavy code, dynamic tests are really great. For if it gets less mathematical, more real world, sometimes it can be difficult, but there are tools available and steadily improving. And if you have a problem with anything, with any object, and you think maybe there should be some tool available for this, you should just ask on the Hypothesis mailing list, for example, because they want to know this. Okay, yeah, thanks for listening. And you get out in time for lunch.
Okay, thank you. Do we have any questions?
Hey, very interesting talk. Maybe this is covered by the custom strategies, but are there provisions for providing templates for example, protocol fuzzing?
No, I think that doesn't exist yet.
Okay, thanks.
Thanks for the talk. Do any interesting bugs come to mind that you found in your production code base?
Yes. We had one combinatorial optimization algorithm which would only fail, so as input it would take some distributions that we predicted, and it would only fail if there are 2 degenerate distributions and at least 1 non-degenerate distribution. In that case, it would enter an infinite loop.
So it was data you weren't expecting, or could you have hard-coded that if you thought really hard about it, as an example?
Sorry?
Was that data you were expecting, or if you'd been hard-coding your examples, might you have come up with that?
No. No. I think we would have never come up with that ourselves.
Cool.
Any more questions? No? Okay. Please join me in thanking our speaker once again.
Thank you. A bit fast.